Welcome to Sleepy Science Odyssey. Tonight, the stars, distant suns burning across billions of years, scattered through the darkness in numbers beyond counting, will move slowly through their births, their lives, and their deaths. From the smallest red dwarfs to the most massive blue giants, from clouds of dust to white dwarfs cooling in the dark. We'll explore how stars form, how they shine, how they change, and what happens when their fuel runs out. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real science, no hype, just quiet facts in the dark. Let's begin. Stars are massive balls of gas held together by their own gravity. At their core, the pressure and temperature are so extreme that hydrogen atoms fuse into helium, releasing enormous amounts of energy. This process, called nuclear fusion, is what makes stars shine. The energy travels outward from the core, eventually reaching the surface and radiating into space as light and heat. Without gravity, a star would simply expand and disperse into space like steam from boiling water. Without fusion, it would collapse under its own weight, crushed by gravity into an ever-denser ball. Stars exist in a delicate balance between these two forces, gravity pulling inward, pressure from fusion pushing outward, and that balance can last for billions of years. The equilibrium is so precise that even small changes in temperature or pressure are self-correcting. If the core gets hotter, fusion speeds up, pressure increases, and the core expands slightly, cooling it back down. If it gets cooler, the opposite happens. This thermostat keeps stars stable throughout most of their lives. The sun is a star, and it's actually quite ordinary. We think of the sun as special because it's our star, the source of all light and warmth on Earth, the center of our solar system, the reason life exists on this planet. But in cosmic terms, the sun is thoroughly average. It's a G-type main sequence star, sometimes called a yellow dwarf. Though it's actually white when viewed from space, our atmosphere makes it appear yellow. There are stars much larger, much hotter, and much brighter than the sun. Betelgeuse, for example, is nearly 1,000 times the sun's diameter. There are also stars much smaller, cooler, and dimmer. Red dwarfs can be 1/10 the sun's mass and emit only 1/10,000th of its light. The sun sits somewhere in the middle of this vast range, unremarkable in the grand catalogue of stars. It's a perfectly average, middle-aged, medium-sized star, but its very ordinariness is what makes it valuable for understanding stellar physics. And its stability, burning steadily for about 4.6 billion years without major fluctuations, is what allowed life to develop on Earth. Planets orbiting more variable stars would experience dramatic climate swings that might prevent complex life from evolving. The sun's boring, predictable nature is exactly what we need. Stars come in different colors, and those colors tell us their temperature. The coolest stars glow red, with surface temperatures around 3,000 Kelvin. That's still about half the temperature of the sun's surface, but in stellar terms, it's relatively cool. Hotter stars appear orange or yellow like the sun, with temperatures around 5,800 Kelvin. Even hotter stars shine white or blue-white, with surface temperatures reaching 10,000 Kelvin or more. The hottest stars are blue, with temperatures exceeding 30,000 Kelvin, more than 5 times the sun's surface temperature. These colors aren't arbitrary or coincidental. They're a direct indication of how much energy the star is producing and how hot its surface is. The relationship between color and temperature is described by Wien's displacement law, which states that hotter objects emit light with shorter wavelengths. Blue light has a shorter wavelength than red light, so blue stars are hotter than red stars. When astronomers look at a star's color, they're essentially taking its temperature from light years away. Blue stars burn hot and bright, consuming their fuel rapidly. Red stars burn cool and dim, sipping their fuel slowly. The color tells you not just the temperature, but also hints at the star's mass, its age, and how long it will live. Color is one of the most fundamental properties we can measure, and it unlocks a wealth of information about a star's nature. The closest star to Earth after the Sun is Proxima Centauri. It's about 4.24 light-years away, which means light from Proxima Centauri takes 4.24 years to reach us. When you look at that star through a telescope, you're seeing it as it was over 4 years ago. If something dramatic happened to Proxima Centauri today, if it exploded or suddenly brightened, we wouldn't know for more than 4 years. The light carrying that information is still traveling through space, crossing the vast emptiness between us. Proxima Centauri is a red dwarf, much smaller and cooler than the Sun. It has only about 12% of the Sun's mass and is about 1/7 its diameter. Its luminosity is less than 0.2% of the Sun's. You'd need hundreds of Proxima Centauris to equal the Sun's light output. Despite being the closest star to us, Proxima Centauri is so faint you can't see it with the naked eye. You need a telescope, even a small one, to observe it. The nearest star visible without a telescope is actually Alpha Centauri A, one of the other stars in the Alpha Centauri system, slightly farther away at about 4.37 light-years. The Alpha Centauri system is a triple star system, 3 stars bound together by gravity, orbiting each other. Proxima Centauri orbits the other 2 at a great distance, taking about 500,000 years to complete one orbit. In 2016, astronomers discovered a planet orbiting Proxima Centauri, called Proxima Centauri b. It's slightly more massive than Earth and orbits in the star's habitable zone, where liquid water could exist. Whether it actually has water, or an atmosphere, or any chance of supporting life, remains unknown. But it's the closest exoplanet to Earth, and it's orbiting the closest star. That proximity makes it a prime target for future observations and perhaps, someday, an interstellar probe. Stars are born in massive clouds of gas and dust called nebulae. These clouds, mostly hydrogen and helium left over from the Big Bang, along with heavier elements from previous generations of stars, can stretch for hundreds of light-years. They're among the largest structures in galaxies, vast regions where gas drifts slowly through space. Gravity slowly pulls the gas together, and as it does, the cloud begins to fragment into denser clumps. These clumps continue to collapse, pulled inward by their own gravity. As a clump collapses, it heats up. This might seem counterintuitive. Shouldn't something get cooler as it expands, not hotter as it contracts? But gravitational compression converts potential energy into thermal energy. The gas particles move faster, collide more frequently, and the temperature rises. Eventually, the center becomes so hot and dense that hydrogen atoms begin to fuse into helium. When fusion ignites, a star is born. The process isn't instant. It can take millions of years for a star to form from a collapsing cloud. A solar mass star takes about 10 million years from initial collapse to ignition. More massive stars form faster, in as little as 100,000 years, because their greater gravity accelerates the collapse. Less massive stars take longer, sometimes 100 million years or more. But once fusion begins, the star settles into a stable state, burning hydrogen in its core for the majority of its life. The remaining gas and dust that didn't fall into the star often forms a disk around it, from which planets can form. This is how our solar system began, as a collapsing cloud 4.6 billion years ago, with the Sun forming at the center and the planets coalescing from the leftover disk. Not all stars form alone. Many stars are born in groups, sometimes hundreds or thousands at a time, in regions called stellar nurseries or star-forming regions. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery only about 1,350 light-years away. Within it, hundreds of young stars have formed in the past million years, and more are still forming today. When you look at the Orion Nebula through a telescope, you're watching the birth of stars in real time. Well, in real time, as it was 1,350 years ago. Over time, these groups of newborn stars can drift apart. The gravitational influence of the galaxy and close encounters with other stars gradually disperse the cluster. In a few tens of millions of years, the stars that form together may be scattered across different parts of the galaxy with no obvious connection to each other, but some stay together as star clusters. The Pleiades, a cluster visible to the naked eye as a tight group of stars, contains several hundred stars born from the same cloud of gas. They're young, only about 100 million years old, and they're still relatively close together, orbiting through the galaxy as a group. Eventually, even the Pleiades will disperse, but for now they remain a family. Other clusters, called globular clusters, contain hundreds of thousands of stars packed into a spherical region only a few dozen light-years across. These clusters are ancient, some of the oldest structures in the galaxy, with ages of 10 to 13 billion years. The stars in globular clusters are so old they've been orbiting the galaxy since shortly after it formed. They're living fossils, witnesses to the early universe. The lifespan of a star depends on its mass. This is one of the most fundamental principles in stellar astronomy. Massive stars burn through their fuel quickly. A star 20 times the mass of the Sun might only live for a few million years. That sounds like a long time by human standards, but it's nothing in cosmic terms. The dinosaurs existed for longer than a massive star lives. These massive stars burn hot and bright, fusing hydrogen at an incredible rate. They shine with the luminosity of tens of thousands of suns, pouring energy into space. And then they die young, exploding as supernovae in spectacular fashion. Smaller stars, like red dwarfs, burn their fuel slowly and can live for trillions of years, far longer than the current age of the universe. The smallest red dwarfs are so miserly with their fuel that they could, in theory, burn for 10 trillion years. For comparison, the universe is only about 13.8 billion years old. These tiny stars will outlast everything else, still shining long after all the massive stars have died, after the galaxies have gone dark, after the universe has aged beyond recognition. The Sun, with its medium mass, will live for about 10 billion years in total. It's currently about 4.6 billion years old, which means it's nearly halfway through its life. In another 5 billion years, the Sun will exhaust the hydrogen in its core and begin to change. The relationship between mass and lifespan is counterintuitive. You might think a more massive star, with more fuel, would live longer. But massive stars burn so much hotter that they consume their fuel far faster than their extra mass can compensate for. It's like comparing a compact car with a small gas tank to a sports car with a large tank. The sports car has more fuel, but it burns through it so quickly that it runs out first. Mass determines almost everything about a star: its temperature, its brightness, its color, its lifespan, and its ultimate fate. Stars spend most of their lives on the main sequence. This is the phase where they fuse hydrogen into helium in their cores, the stable, long-lasting period that defines a star's existence. For the Sun, this phase lasts about 10 billion years. For a massive star, it might be only a few million years. For a red dwarf, it could be trillions. But regardless of the absolute duration, stars spend about 90% of their lives on the main sequence. During this time, the star is remarkably stable. The outward pressure from fusion balances the inward pull of gravity, and the star doesn't change much. It sits at a consistent brightness and temperature, steadily converting hydrogen into helium, day after day, year after year, eon after eon. Astronomers classify stars by where they fall on the main sequence, which is represented on a diagram called the Hertzsprung-Russell diagram. This plots a star's brightness against its temperature, and most stars fall along a diagonal line from hot, bright stars in the upper left to cool, dim stars in the lower right. This line is the main sequence, and it represents stars in the prime of their lives, burning hydrogen. The main sequence is the longest phase of a star's life by far. Everything that comes after the red giant phase, the planetary nebula, the white dwarf, or the supernova and neutron star, is much briefer, sometimes only a few million years or less. The main sequence is the default state of a star, the condition in which it spends most of its existence. It's the stellar equivalent of adulthood, the long, productive period between formation and decline. When a star runs out of hydrogen in its core, it begins to change. This is the beginning of the end, though the process can take hundreds of millions of years. Once the core has fused all its hydrogen into helium, fusion stops. Without fusion, there's no outward pressure to balance gravity. The core contracts, and as it does, it heats up. Again, gravitational compression converts potential energy to heat. The temperature rises until it's hot enough to fuse hydrogen in a shell around the inert helium core. This shell burning is less efficient than core burning, but it produces enough energy to dramatically change the star. The outer layers expand, ballooning outward to many times the star's original size. The star becomes a red giant. For a star like the Sun, this expansion is dramatic. The Sun will swell to perhaps 100 times its current diameter, possibly engulfing Mercury and Venus, and maybe even reaching Earth's orbit. The exact extent is uncertain, but it's clear that the inner solar system will be radically transformed. The Sun's surface will cool, giving it a reddish color, but it will shine much brighter because it's so much larger. Surface area matters. A cool, large star can be more luminous than a hot, small one. During this phase, if the core gets hot enough, about 100 million Kelvin, it can begin fusing helium into heavier elements like carbon and oxygen. This helium fusion occurs through a process called the triple alpha process, where 3 helium nuclei combine to form carbon. The helium-burning phase doesn't last as long as the hydrogen-burning phase, only a few 100 million years for a star like the Sun. The star is burning through its reserves, approaching the end of its life. The red giant phase is beautiful but temporary, a brief flare-up before the final fade. The core of a star is where all the fusion happens. The temperature and pressure are highest here, at the very center, where the full weight of the star presses down. In the Sun's core, temperatures reach about 15 million Kelvin. The pressure is about 250 billion times Earth's atmospheric pressure at sea level. At these extreme conditions, hydrogen nuclei, protons, collide with enough force to overcome their natural repulsion. Protons are positively charged, and like charges repel, but in the core of a star, they're moving so fast and are squeezed so tightly that they can get close enough for the strong nuclear force to take over and bind them together. When 4 hydrogen nuclei fuse to form 1 helium nucleus, a small amount of mass is converted to energy according to Einstein's equation, E equals mc2. That small amount of mass, multiplied by the speed of light squared, equals an enormous amount of energy. The energy is released initially as gamma rays, the highest energy form of light. But these gamma rays don't travel straight out of the star. The core is incredibly dense, and the gamma rays are immediately absorbed by nearby atoms. Those atoms re-emit the energy, but at slightly lower energy. This absorption and re-emission happens countless times. The gamma rays are scattered, absorbed, and re-emitted, gradually losing energy and transforming into lower energy photons, X-rays, ultraviolet light, visible light, infrared. It can take tens of thousands of years, perhaps up to 100,000 years, for the energy produced in the core to reach the surface and escape as visible light. The photons we see from the sun were created in the core when mammoths still roamed the Earth. The core is the engine, but the journey from core to surface is long and tortuous. By the time the light reaches us, it has been transformed many times, carrying information about the star's interior encoded in its spectrum. Stars don't just produce light, they produce elements. Hydrogen fusion creates helium. That's the first step, the reaction that powers most of a star's life. But in more massive stars, or in stars in later stages of their lives, fusion continues beyond helium. Helium fusion creates carbon and oxygen. 3 helium nuclei can fuse to form 1 carbon nucleus. Carbon and oxygen can then fuse to create neon, magnesium, and other elements. Silicon fusion produces iron. Each step in this chain releases energy, but each step also requires higher temperatures and pressures to occur. Helium fusion requires about 100 million Kelvin. Carbon fusion requires about 600 million Kelvin. Silicon fusion requires over 2 billion Kelvin. Only the most massive stars can reach these temperatures in their cores. Stars like the Sun will never fuse elements heavier than carbon and oxygen. They simply don't have enough mass to generate the necessary conditions. But stars with more than about 8 times the Sun's mass can fuse elements all the way up to iron. Iron is the end of the line. It has the most stable nucleus of any element, and fusing iron doesn't release energy, it consumes energy. Once a massive star's core fills with iron, fusion stops. There's no more energy being produced to hold up the star against gravity. Without the outward pressure from fusion, gravity takes over completely, and the core collapses in a fraction of a second. This catastrophic collapse triggers a supernova, one of the most violent events in the universe. The supernova scatters the elements the star created, carbon, oxygen, silicon, iron, and many others, into space, enriching the interstellar medium. These elements become part of the next generation of stars and planets. Every atom in your body heavier than hydrogen was created inside a star and scattered by a supernova. You are made of stardust, quite literally. Red dwarfs are the most common type of star. They make up about 75% of all stars in the Milky Way, possibly more. Red dwarfs are small, cool, and dim, with masses less than half the Sun's and often much less. The smallest red dwarfs are only about 8% of the Sun's mass, just barely massive enough to sustain hydrogen fusion. Below that mass, you get brown dwarfs, which aren't quite stars. Red dwarfs burn hydrogen so slowly, mixing their entire mass through convection, that they can live for trillions of years. Some estimates suggest the smallest red dwarfs could live for 10 trillion years or more. The universe isn't old enough yet for any red dwarf to have died of old age. Every red dwarf that has ever formed is still shining. They're the tortoises of the stellar world, slow and steady, outlasting everything else. Red dwarfs are also much smaller than the Sun, typically 1/7 to 1/2 the Sun's diameter. This makes them incredibly dense for their mass. Despite being the most common stars, red dwarfs are so faint that not a single one is visible to the naked eye from Earth. The brightest red dwarf, Lacal 8760, is only magnitude 6.6, just barely at the limit of naked eye visibility under perfect conditions. Most are much fainter. If you replace the Sun with a typical red dwarf, Earth would be plunged into permanent twilight, receiving only a fraction of the light and heat we currently enjoy. But red dwarfs have their advantages. Their longevity means planets orbiting them have a long time for life to evolve. And because red dwarfs are so common, there are many potential homes for life in the galaxy. The challenge is that planets need to orbit very close to red dwarfs to be warm enough for liquid water, and close orbits mean the planets are subjected to intense stellar flares and tidal locking. Still, red dwarfs represent the majority of possible homes for life, simply because they're so numerous. Blue giants are rare, but they're among the brightest stars. They're massive, often more than 10 times the mass of the Sun, and they burn extremely hot. Their surface temperatures can exceed 30,000 Kelvin, giving them a brilliant blue color. Blue giants are so luminous they can be seen from enormous distances. Rigel, the brightest star in the constellation Orion, though technically not a blue giant but a blue supergiant, is about 860 light-years away and shines with the luminosity of 120,000 suns. It's visible from Earth as a bright blue-white star, one of the most striking objects in the night sky. Blue giants don't live long. Their immense mass means they burn through their fuel in just a few million years. In cosmic terms, they're brief, brilliant flares in the darkness. Many blue giants are young, recently formed from massive clouds of gas. They often still have remnants of their birth clouds around them, glowing nebulae illuminated by the intense ultraviolet radiation from the hot star. When blue giants die, they do so spectacularly, exploding as supernovae and leaving behind neutron stars or black holes. Because they're so luminous, blue giants can be used as markers for measuring distances to other galaxies. If you spot a blue giant in a distant galaxy, you know roughly how bright it should be, and by comparing that to how bright it appears, you can calculate the distance. Blue giants are stellar beacons, visible across millions of light-years, announcing their presence and illuminating the structure of galaxies. Some stars don't shine steadily, they pulse. Cepheid variables are a type of star that expands and contracts rhythmically, changing brightness as they do. The star swells up, becoming larger and brighter, then contracts, becoming smaller and dimmer in a regular cycle that can last from days to months. Delta Cephei, the star that gave the class its name, has a period of about 5.4 days. It varies in brightness by about a factor of 2 over this cycle. The pulsation is driven by instabilities in the star's outer layers. As the star contracts, the layers heat up and become more opaque, trapping radiation. The pressure builds until the layers expand again. As they expand, they cool and become more transparent, allowing radiation to escape. The pressure drops and the layers contract again. This cycle repeats endlessly. The most important property of Cepheid variables is that the period of pulsation is directly related to the star's intrinsic brightness, its absolute magnitude. A Cepheid that pulses every 10 days is brighter than one that pulses every 3 days. This relationship, discovered by Henrietta Leavitt in 1912, is incredibly useful for measuring distances. By measuring a Cepheid's pulsation period, astronomers can determine its true brightness. Comparing that to how bright it appears from Earth tells them how far away it is. Cepheids are cosmic distance markers, allowing astronomers to measure distances across millions of light-years. They were the key to Edwin Hubble's discovery that Andromeda was a separate galaxy far beyond the Milky Way. Cepheids are still used today to calibrate the cosmic distance ladder, the series of techniques used to measure distances to ever more remote objects in the universe. Binary stars are pairs of stars orbiting each other. About half of all stars, possibly more, are part of binary or multiple star systems. They're bound together by gravity, orbiting a common center of mass. Sometimes the stars are close together, orbiting in days or hours, so close they're nearly touching. Other times they're far apart, taking centuries or even millennia to complete one orbit, separated by distances larger than our solar system. In close binaries, the stars can exchange material. Gas from one star can overflow and flow onto its companion, creating an accretion disk and sometimes triggering bursts of fusion on the surface of the receiving star. These systems can produce novae, sudden brightenings caused by runaway fusion on a white dwarf surface. In extreme cases, if enough mass accumulates on a white dwarf, it can exceed the Chandrasekhar limit and explode as a type Ia supernova, completely destroying the star. Binary systems give us unique insights into stellar masses and evolution. By observing the orbit of a binary pair, we can use Kepler's laws to calculate the masses of both stars. This is one of the few ways to directly measure stellar masses. Binary systems also let us observe stellar interactions that don't occur in isolated stars. Some binaries eclipse each other from our point of view. As one star passes in front of the other, the system's brightness dips. By carefully studying these eclipses, we can determine the sizes, temperatures, and even the shapes of the stars. Binary systems are laboratories for stellar physics, revealing processes that would remain hidden in single stars. Neutron stars are the remnants of massive stars that exploded. When a star much more massive than the Sun dies in a supernova, its core collapses into an incredibly dense object. The protons and electrons are crushed together, forming neutrons in a process that's almost incomprehensible. What's left is a neutron star, a sphere about 20 kilometers across, roughly the size of a city, but containing more mass than the Sun. Neutron stars are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you could somehow bring that teaspoon to Earth, it would instantly sink through the ground, falling toward the center of the planet. Neutron stars have surface gravities about 200 billion times stronger than Earth's. If you stood on a neutron star, which you couldn't, you'd weigh billions of times more than you do on Earth. A fall of 1 millimeter would accelerate you to a significant fraction of the speed of light. Neutron stars push physics to its limits. They're made almost entirely of neutrons packed together at nuclear densities, with a thin atmosphere only a few centimeters thick. The interior structure is still debated. There may be layers of exotic forms of matter, including superfluids and possibly even quark matter at the very core. Neutron stars have the strongest magnetic fields known in the universe, trillions of times stronger than Earth's. They're cosmic laboratories where matter exists in states that can't be replicated anywhere else. And they're relatively common. There are probably hundreds of millions of neutron stars in the Milky Way, though most are difficult to detect because they're so small and emit little visible light. Some neutron stars spin incredibly fast. These are called pulsars. As they rotate, they emit beams of radiation from their magnetic poles, like a lighthouse. If one of those beams sweeps past Earth, we detect a pulse of light or radio waves. The fastest pulsars rotate hundreds of times per second. One pulsar, PSRJ 1748-2446 AD, spins 716 times per second. That's faster than a kitchen blender, faster than most turbine engines. And remember, this is an object the size of a city with more mass than the Sun. At that rotation rate, the surface of the pulsar is moving at about 1/4 the speed of light. Material on the equator is held down only by the immense gravity, any slower gravity, and it would be flung off into space by centrifugal force. Pulsars are incredibly precise clocks. Some pulsars are so regular that they rival atomic clocks in accuracy. The millisecond pulsars, which spin hundreds of times per second, are especially stable. They can be used to detect gravitational waves through pulsar timing arrays, where astronomers monitor the arrival times of pulses from multiple pulsars and look for correlated changes that would indicate a gravitational wave passing through the galaxy. Pulsars were discovered accidentally in 1967 by Jocelyn Bell Burnell, then a graduate student. At first, the regular pulses were so precise that they were jokingly called LGM-1 for little green men, the idea being they might be signals from an alien civilization. It was soon realized that the signals came from rapidly rotating neutron stars, but the discovery opened a new window into extreme physics. Pulsars have been used to test general relativity, study the interstellar medium, discover exoplanets, and even serve as natural GPS satellites for potential interstellar navigation. White dwarfs are what stars like the Sun become at the end of their lives. After the Sun swells into a red giant and sheds its outer layers, all that's left is the core, a white dwarf. It's incredibly dense, about the size of Earth, but with half the mass of the Sun. A white dwarf doesn't produce energy through fusion anymore. All the hydrogen, helium, and other fusionable material has been consumed or expelled. It's simply a hot, dense ball of carbon and oxygen, the ashes of billions of years of fusion, slowly cooling over billions more years. It glows white-hot at first, with surface temperatures around 100,000 Kelvin or more, far hotter than the Sun's surface. But with no internal energy source, it gradually radiates away its stored heat. Over billions of years, it will fade, first to yellow, then red, then brown, then black. Eventually, it will become a black dwarf, a cold, dark cinder, essentially a stellar corpse. No black dwarfs exist yet. The universe isn't old enough. Even the oldest white dwarfs, formed 10 billion years ago or more, are still warm enough to glow faintly. It will take tens of billions or even hundreds of billions of years for a white dwarf to cool completely. White dwarfs are supported not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed into the same state. This pressure can support a white dwarf up to about 1.4 solar masses, the Chandrasekhar limit. Beyond that mass, even electron degeneracy pressure can't hold it up, and the white dwarf will collapse, usually triggering a supernova. White dwarfs are the fate of most stars in the galaxy. About 97% of all stars, including the Sun, will end as white dwarfs. They're the final chapter in the story of ordinary stars, quiet endings to lives that may have lasted billions of years. The Hertzsprung-Russell diagram organizes stars by temperature and brightness. Created independently by Ejnar Hertzsprung and Henry Norris Russell in the early 1900s, this diagram is one of the most important tools in astronomy. On the vertical axis is luminosity, the total amount of energy a star emits. On the horizontal axis is temperature, usually with hotter stars on the left and cooler on the right. When you plot thousands of stars on this diagram, clear patterns emerge. Most stars fall along a diagonal band from hot, bright stars in the upper left to cool, dim stars in the lower right. This band is the main sequence, where stars spend most of their lives fusing hydrogen in their cores. The position of a star on the main sequence tells you its mass. More massive stars are hotter and brighter, appearing toward the upper left, while less massive stars are cooler and dimmer toward the lower right. Giants and supergiants occupy the upper right, cool but extremely luminous because they're so large. White dwarfs sit in the lower left, hot but very dim because they're so small. The diagram reveals patterns in stellar evolution. A star's path through the diagram over its lifetime traces its evolutionary track. It starts on the main sequence, moves to the right and up as it becomes a red giant, then drops down and to the left as it becomes a white dwarf. By plotting a star on the HR diagram, astronomers can infer its age, mass, stage of life, and eventual fate. The diagram is a map of stellar existence, showing how stars of different masses and ages relate to each other. It's taught in every introductory astronomy course because it elegantly captures the fundamental properties and life cycles of stars. Stars are not evenly distributed across space. They cluster together in galaxies, and within galaxies, they concentrate in certain regions. Our galaxy, the Milky Way, contains between 100 and 400 billion stars. They're not spread uniformly. Most are concentrated in the galactic disk, a flat spiral about 100,000 light-years across and only about 1,000 light-years thick. The density of stars in the solar neighborhood is about 0.14 stars per cubic light-year. That might not sound like much, and it isn't. Space is mostly empty. But near the galactic center, the density is thousands of times higher. In the very center, within a light-year of the supermassive black hole, millions of stars are packed together. The night sky from a planet there would be filled with bright stars. Thousands of them brighter than Venus appears from Earth. The sky would never be truly dark. In the galactic halo, the density drops to almost nothing, with some regions containing only a handful of stars per 1,000 cubic light-years. The distribution of stars reflects the galaxy's structure and history. The disk is where active star formation occurs, where gas clouds collapse and new stars ignite. The halo contains old stars, some of the first generation formed when the galaxy was young. The Sun sits in one of the spiral arms, about 26,000 light-years from the galactic center. From Earth, we see the Milky Way as a band of light across the night sky, the combined glow of billions of stars too distant to resolve individually. When you look at the Milky Way on a dark night, you're looking edge-on through the galactic disk, seeing the accumulated light of countless suns. Not all starlight reaches us. Interstellar dust, tiny grains of carbon and silicate only a few microns across, absorbs and scatters light as it travels through space. This is why distant stars often appear redder than they truly are. The dust scatters blue light more efficiently than red, like how Earth's atmosphere scatters blue light during the day, making the sky blue. When light from a star passes through dust clouds, the blue light is scattered away, and the red light continues. This is called interstellar reddening. It's the same effect that makes sunsets red on Earth. The atmosphere scatters blue light, leaving the red to reach our eyes. Astronomers must account for this reddening when studying distant stars, correcting for the dust between us and them to determine the star's true color and temperature. The amount of reddening tells us how much dust is in the line of sight, which helps map the distribution of dust in the galaxy. Dust also emits infrared light when warmed by starlight, creating a diffuse glow visible to infrared telescopes. This dust glow can sometimes be brighter than the stars themselves, making the galaxy look very different in infrared compared to visible light. Understanding interstellar dust is crucial for accurate measurements of stellar properties and distances. It's a veil between us and the universe, one we must learn to see through. The North Star, Polaris, is not the brightest star in the sky. It's only the 48th brightest, far dimmer than stars like Sirius, Canopus, or Rigel. But it's special because it sits almost directly above Earth's North Pole. As Earth rotates, the entire sky appears to turn around Polaris, with all the other stars tracing circles around it. To observers in the northern hemisphere, Polaris remains nearly fixed in position, a reliable marker for finding north. It's been a navigational tool for centuries, used by sailors, travelers, and explorers to orient themselves. The altitude of Polaris above the horizon equals the observer's latitude. If you're at 40 degrees north latitude, Polaris appears 40 degrees above the horizon. This makes it invaluable for navigation. Polaris is actually a multiple star system. The primary star is a supergiant, much brighter and larger than the Sun, about 2,500 times more luminous. It's about 430 light-years away. Polaris is also a Cepheid variable, pulsating slightly with a period of about 4 days, though the pulsations are small and not noticeable to the naked eye. In about 12,000 years, due to the precession of Earth's axis, a slow wobble in Earth's rotation, Polaris will no longer be the North Star. Another star, Vega, will take its place. Then, in another 14,000 years, Polaris will return to its position as the North Star. This cycle repeats every 26,000 years, a consequence of the gravitational pull of the Sun and Moon on Earth's equatorial bulge. For now, Polaris holds the title, a constant point in a turning sky. Betelgeuse, a red supergiant in the constellation Orion, is nearing the end of its life. It's one of the largest stars visible to the naked eye, with a diameter about 1,000 times that of the Sun. If you placed Betelgeuse at the center of our solar system, its surface would extend beyond the orbit of Mars, possibly reaching Jupiter. Despite its enormous size, Betelgeuse is not particularly massive for a supergiant, about 20 times the Sun's mass. Its low density means it's more like a hot, thin atmosphere than a solid object. Betelgeuse is expected to explode as a supernova sometime in the next 100,000 years. That might sound like a long time, but in astronomical terms, it's imminent. The star could explode tomorrow or 50,000 years from now. We don't know. When it does, it will briefly outshine every other star in the night sky, possibly becoming as bright as the full moon. It will be visible during the day, a brilliant point of light near the Sun. After a few weeks or months, it will fade, leaving behind a rapidly expanding cloud of gas, and at the center, either a neutron star or a black hole. We're watching a star in its final moments, though those moments could still last millennia. Betelgeuse is about 650 light-years away, so if it exploded 649 years ago, the light from the explosion would reach us next year. We'd have no warning. One night, we'd go to bed with Orion looking as it always has. The next night, there'd be a brilliant new star, brighter than anything else in the sky. Astronomers around the world would scramble to observe it, capturing the supernova's light with telescopes across the spectrum. It would be one of the most significant astronomical events in human history, a nearby supernova visible to the naked eye. The last time this happened was in 1987, when a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, was visible from the southern hemisphere. Before that, the most famous was Kepler's supernova in 1604. A Betelgeuse supernova would be the closest and brightest in over 400 years. The star Sirius is the brightest star in Earth's night sky. It's only 8.6 light-years away, relatively close in cosmic terms, one of the nearest star systems to Earth. Sirius is actually a binary system, consisting of two stars orbiting each other. The main star, Sirius A, is about twice the mass of the Sun and 25 times more luminous. It's a hot, white star with a surface temperature of about 9,940 Kelvin, significantly hotter than the Sun. Its companion, Sirius B, is a white dwarf, the remnant of a star that died long ago. Sirius B is about the mass of the Sun, but only about the size of Earth, making it incredibly dense. A teaspoon of Sirius B would weigh several tons. The two stars orbit each other every 50 years, with their closest approach bringing them as near as the distance between the Sun and Uranus. Sirius has been known since ancient times. In ancient Egypt, the heliacal rising of Sirius, its first appearance in the dawn sky after being hidden by the sun, marked the flooding of the Nile, a crucial event for agriculture. The Egyptians built their calendar around Sirius. In ancient Greece, Sirius was associated with the dog days of summer, the hottest part of the year when Sirius rises with the sun. The name Sirius comes from the Greek word for glowing or scorcher. The star is so prominent that it features in mythology and astronomy across many cultures. Today, Sirius is used as a reference point for measuring the brightness of other stars. Its brightness and proximity make it an important object for studying stellar evolution, white dwarfs, and binary star dynamics. Some stars are so large they're called hypergiants. These are the most massive and luminous stars known. VY Canis Majoris, a red hypergiant, has a radius about 1,400 times that of the Sun. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, possibly reaching Saturn. The star is so large that light takes more than 6 hours to travel from one side to the other. For comparison, light takes only 8 minutes to travel from the Sun to Earth. Hypergiants are incredibly rare. Only a few are known in the Milky Way. They're so luminous that they can be seen from millions of light years away, beacons shining across the galaxy. These stars are incredibly unstable. They lose mass through intense stellar winds, shedding solar masses of material every year. VY Canis Majoris is surrounded by a nebula of ejected material, visible in infrared images. The star is literally tearing itself apart, unable to hold itself together against its own luminosity. Hypergiants don't live long. Their immense mass means they burn through their fuel in just a few million years. When they die, they explode as supernovae, possibly creating some of the most massive black holes known. The physics of hypergiants is still poorly understood. They exist at the edge of what's possible for a star, where radiation pressure, gravity, and mass loss all balance precariously. Studying them helps astronomers understand the limits of stellar existence and the processes that govern the most extreme stars. Stars are moving through space, though we don't usually notice. Their motion relative to the Sun is called proper motion, and over centuries or millennia, it causes the patterns of constellations to slowly shift. The stars in the Big Dipper, for example, are not gravitationally bound to each other. They're drifting in different directions. In 100,000 years, the Big Dipper will look completely different, its familiar shape distorted beyond recognition. Barnard's star, a red dwarf only 6 light-years away, has the largest proper motion of any star, moving across the sky at a rate noticeable over a human lifetime. It shifts position by about 10 arcseconds per year, which sounds small but adds up. In about 10,000 years, Barnard's star will be closer to Earth than any other star, briefly becoming our nearest stellar neighbor before drifting away again. Stars also move toward or away from us, motion we can detect through the Doppler shift in their spectra. If a star is moving toward us, its light is blue-shifted to shorter wavelengths. If it's moving away, the light is redshifted. By measuring these shifts, astronomers can map the three-dimensional motions of stars. The Sun itself is moving through space at about 20 kilometers per second relative to nearby stars, heading in the general direction of the constellation Hercules. This motion is called the solar apex. All these motions are part of the galaxy's rotation and the random velocities of stars within it. Over millions of years, the face of the night sky changes completely as stars drift past each other. their motions slowly rearranging the familiar patterns we see today. The light from stars takes time to reach us, so we see them as they were in the past. When you look at a star 100 light-years away, you're seeing light that left that star a century ago. If that star exploded 50 years ago, you wouldn't know yet. The explosion's light is still traveling through space, crossing the vast emptiness between us. It might arrive tomorrow, or next year, or decades from now, depending on when the explosion occurred. The farther away a star is, the further back in time you're looking. When we observe distant galaxies, we see them as they were millions or even billions of years ago. Astronomy is a form of time travel, allowing us to study the universe's past. Every photon that enters our telescopes is a messenger from history, carrying information about distant suns as they were when the light left them. This also means that the night sky is a mixture of different moments. Some stars you see tonight are as they were a few years ago. Others are as they were centuries or thousands of years ago. The constellations are not snapshots of a single moment, but composites of many different times, layered together by the speed of light. If aliens in a distant galaxy are looking at Earth right now, they're not seeing us as we are. They're seeing Earth as it was when their light left us, perhaps when dinosaurs roamed, or when the first humans were learning to walk upright, or even before multicellular life existed, depending on how far away they are. We're all looking into each other's pasts, separated by the vast distances of space and the finite speed of light. Variable stars change brightness over time. Some, like eclipsing binaries, dim periodically when one star passes in front of the other, blocking its light. These aren't intrinsically variable. The stars themselves aren't changing, but from our perspective, the system's brightness changes as the stars eclipse each other. Other variable stars are intrinsically variable, their brightness changing due to processes within the star itself. Mira variables, named after the star Mira in the constellation Cetus, pulsate over periods of months or years, swelling and shrinking as they age. Mira itself varies in brightness by a factor of 1,000 over about 11 months, sometimes becoming visible to the naked eye and then fading to invisibility. These pulsations are driven by instabilities in the star's outer layers, similar to Cepheids, but on a longer timescale. Eruptive variables undergo sudden brightenings due to instabilities or mass transfer in binary systems. Novae and supernovae are extreme examples, where a star suddenly brightens by factors of millions or billions. Other stars, like T-Tauri variables, are young and still contracting, with brightness variations caused by changing accretion rates and magnetic activity. Studying variable stars provides insights into stellar structure, evolution, and binary interactions. They're natural experiments, revealing processes that would be hidden in non-variable stars. Variable star observations have been crucial for understanding stellar physics and for measuring cosmic distances. Amateur astronomers contribute significantly to variable star science through organizations like the American Association of Variable Star Observers, which has collected millions of observations over more than a century. Brown dwarfs are failed stars. They form like stars from collapsing clouds of gas, but they never accumulate enough mass to ignite hydrogen fusion in their cores. They're typically less than 8% the mass of the Sun, which is the minimum mass required to sustain hydrogen fusion. Brown dwarfs do produce some heat from their initial gravitational collapse and from fusing small amounts of deuterium, a heavier isotope of hydrogen. Deuterium fusion occurs at lower temperatures than regular hydrogen fusion, so brown dwarfs can briefly burn deuterium when they're young. But this fuel is quickly exhausted, and the brown dwarf is left to slowly cool over billions of years. They're not true stars because they lack sustained nuclear fusion, but they're not planets either. They form like stars, not by accretion in a protoplanetary disk. They occupy a strange middle ground between the largest planets and the smallest stars. Brown dwarfs glow faintly in infrared light, slowly radiating away their stored heat. The coolest brown dwarfs have surface temperatures similar to a hot oven, around 250 degrees Celsius. These white dwarfs are nearly invisible, detected only with sensitive infrared telescopes. Brown dwarfs are difficult to study because they're so faint, but they're probably quite common. There may be billions in the Milky Way. They represent a significant but mostly invisible population of objects, neither star nor planet, quietly cooling in the darkness between the stars. Some brown dwarfs have planetary systems, with planets orbiting them just as planets orbit stars. The dividing line between brown dwarfs and planets is blurry and still debated, particularly for objects that form in isolation but have masses below the deuterium-burning limit. The brightest star ever observed was a supernova in 1006 AD. It appeared in the constellation Lupus and was visible during the day for weeks, outshining Venus, the brightest object in the sky after the Sun and Moon. At its peak, the supernova reached a magnitude of about -7.5, bright enough to cast shadows at night. Historical records from China, Japan, Europe, and the Arab world all document this guest star that suddenly appeared and then faded over the following months. It was visible for over 2 years, gradually dimming until it was no longer detectable to the naked eye. The supernova, designated SN 1006, was a type Ia supernova, caused by a white dwarf in a binary system accumulating material from its companion until it exceeded the Chandrasekhar limit and exploded. The explosion completely destroyed the white dwarf, leaving behind only an expanding shell of hot gas. Today, the remnant of SN 1006 is visible through telescopes as a large, faint ring of material still expanding outward at thousands of kilometers per second. It's about 7,200 light-years away. The supernova occurred 7,200 years before 1006 AD, but the light took that long to reach Earth. Supernovae this bright are rare. The last supernova visible to the naked eye was in 1987 in the Large Magellanic Cloud, but it was much fainter than SN 1006, never bright enough to see during the day. Before that, Kepler's supernova in 1604 and Tycho's supernova in 1572 were visible to the naked eye, but also fainter than SN 1006. A supernova as bright as SN 1006 might occur in the Milky Way only once every few centuries. If Betelgeuse explodes, it might rival SN 1006's brightness, depending on its exact distance and the energy of the explosion. Some stars exist in incredibly tight orbits. AM Canum Venaticorum is a binary system where two white dwarfs orbit each other every 17 minutes. That's faster than Earth rotates. The stars are so close that they're almost touching, separated by less than the diameter of Earth. Material flows from one star to the other in a thin stream, spiraling around them in an accretion disk. The system is losing energy through gravitational waves, ripples in spacetime itself, predicted by Einstein's general relativity. As energy is radiated away, the orbit shrinks and the stars spiral closer together. Over time, measured in millions of years, the orbit will continue to decay. Eventually, the two white dwarfs will merge. What happens then depends on their combined mass. If their total mass exceeds the Chandrasekhar limit, the merger will trigger a type Ia supernova, completely destroying both stars in a massive explosion. If the mass is below the limit, they'll merge into a single, more massive white dwarf or possibly a neutron star. Systems like AMCVN are laboratories for testing general relativity in strong gravitational fields. The gravitational waves they emit are too weak and low frequency for current detectors like LIGO, but future space-based detectors like LISA will be able to observe them. Thousands of such systems are expected to be detectable by LISA, providing a new way to study binary evolution and white dwarf physics. These tight binaries are fascinating not just for their extreme properties, but for what they reveal about the final stages of stellar evolution and the ways stars can end their lives. Red giants can be enormous. Antares, a red supergiant in the constellation Scorpius, has a radius about 700 times that of the Sun. If placed at the center of our solar system, it would engulf the orbits of Mercury, Venus, Earth, Mars, and possibly even reach Jupiter's orbit. Despite its size, Antares is not particularly massive, only about 12 times the Sun's mass. Its low density means it's more like a very hot, very tenuous atmosphere than a solid object. If you could fly through Antares, you'd barely notice you were inside a star. The material is so thin it's nearly a vacuum by Earth standards. Yet from a distance, Antares shines brilliantly, one of the brightest stars visible from Earth. Its name comes from Greek, meaning rival of Mars, because its reddish color resembles the planet Mars. Antares is approaching the end of its life. It's fusing helium and heavier elements in its core, working through its remaining fuel. In perhaps a few tens of thousands of years, a blink of an eye in cosmic terms, it will explode as a supernova, briefly outshining the entire Milky Way. The explosion will scatter the elements Antares created, carbon, oxygen, silicon, iron, into space, enriching the interstellar medium and providing raw material for future generations of stars and planets. Antares is about 550 light-years away, so its supernova would be spectacular but not dangerous to Earth. It would appear as a brilliant new star, possibly as bright as the full moon, visible during the day and dominating the night sky for weeks or months. Then it would fade, leaving behind an expanding nebula and at the center, a neutron star or black hole. The Sun's closest stellar neighbor, Proxima Centauri, might have a planet in its habitable zone. In 2016, astronomers discovered Proxima Centauri b, a planet orbiting the star at the right distance for liquid water to exist on its surface. The planet is slightly more massive than Earth, about 1.3 Earth masses, and orbits Proxima Centauri every 11 days. That sounds fast, but Proxima Centauri is a red dwarf, much cooler and dimmer than the Sun. To be in the habitable zone, planets need to orbit close to red dwarfs. Proxima b's orbit is only about 7.5 million kilometers from its star, much closer than Mercury is to the Sun. Despite this proximity, the planet receives only about 2/3 the energy Earth receives from the Sun, putting it near the inner edge of the habitable zone. Whether Proxima b actually has water, or an atmosphere, or any chance of supporting life, remains unknown. Proxima Centauri is a flare star, prone to violent outbursts of radiation that could strip away a planet's atmosphere over time. The planet is also likely tidally locked, with one side always facing the star and the other in permanent darkness. This could create extreme temperature differences that might make the planet inhospitable. On the other hand, an atmosphere might distribute heat, and life could potentially exist in the twilight zone between day and night. The discovery of Proxima b raises tantalizing possibilities. It's the closest exoplanet to Earth, only 4.24 light-years away. If we ever send an interstellar probe, Proxima b would be the most obvious target. Even at relativistic speeds, such a mission would take decades, but it's at least conceivable with future technology. The planet represents both a scientific opportunity and a philosophical question. Is the nearest exoplanet also inhabited? We don't know, but the proximity makes it possible, someday, to find out. Supernova explosions are among the most energetic events in the universe. In a few seconds, a supernova releases more energy than the Sun will produce over its entire 10 billion-year lifespan. The explosion ejects the star's outer layers into space at speeds of up to 30,000 kilometers per second, about 10% the speed of light. The kinetic energy alone is staggering, equivalent to converting multiple solar masses entirely into energy. But the supernova also produces a flood of neutrinos, ghostly particles that barely interact with matter. About 99% of the supernova's energy is carried away by neutrinos, streaming out from the collapsing core. Only about 1% goes into the kinetic energy of the explosion and the light we see. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth picked up about 24 neutrinos from the event. That might not sound like many, but considering how rarely neutrinos interact with matter, the fact that we detected any at all means trillions upon trillions passed through Earth. Those neutrinos arrived hours before the light from the supernova because they escaped from the core immediately, while the light had to work its way out through the star's outer layers. Supernovae are also responsible for creating and dispersing heavy elements. Every atom of gold, silver, uranium, and many other elements on Earth was forged in a supernova billions of years ago, before the solar system formed. The supernova scattered these elements into space, where they eventually became part of the gas cloud that collapsed to form the Sun and planets. Without supernovae, the universe would consist only of hydrogen and helium. There would be no carbon, no oxygen, no iron, none of the elements necessary for planets or life. Supernovae are cosmic forges and distributors, creating the raw materials of existence and spreading them across the galaxy. Not all supernovae are the same. Type Ia supernovae occur in binary systems when a white dwarf accretes material from a companion star and exceeds the Chandrasekhar limit, about 1.4 times the Sun's mass. The white dwarf undergoes runaway fusion, a thermonuclear explosion that completely obliterates the star. Nothing is left behind, no neutron star, no black hole, just an expanding cloud of gas. Type Ia supernovae are remarkably uniform in their brightness because they all occur at roughly the same mass, the Chandrasekhar limit. This makes them excellent, standard candles for measuring cosmic distances. By comparing a Type Ia supernova's intrinsic brightness to how bright it appears, astronomers can calculate its distance. This method was used in the 1990s to discover that the universe's expansion is accelerating, a finding that led to the 2011 Nobel Prize in Physics. Type Ii supernovae occur when a massive star, at least 8 times the Sun's mass, exhausts its fuel and collapses. These supernovae leave behind a remnant, either a neutron star or a black hole. Type Ii supernovae are more common than Type Ia, but they're also more variable in brightness, making them less useful as distance indicators. There are also subtypes, Type Ib and Ike supernovae, which are similar to Type Ii but have lost their outer hydrogen or helium layers before exploding, and electron capture supernovae, which occur in stars at the borderline between those that become white dwarfs and those that explode. Each type reveals different aspects of stellar evolution, and the processes that govern stellar death. Observing supernovae across the universe helps astronomers understand not just how stars die, but also the chemical enrichment of galaxies, the formation of compact objects, and the expansion of the universe itself. Some stars end their lives as black holes. When a star more than about 20 times the Sun's mass dies, its core collapses into a point of infinite density, a singularity, surrounded by an event horizon from which nothing, not even light, can escape. This is a black hole. The collapse happens in less than a second, one of the most catastrophic events imaginable. The outer layers of the star explode as a supernova, scattering material into space, but the core implodes, compressed by gravity beyond all resistance. Not even neutron degeneracy pressure, which supports neutron stars, can halt the collapse. The core falls inward, through the density of a neutron star, through all known states of matter, until general relativity predicts it forms a singularity. Black holes don't emit light, so they're invisible. We detect them by observing their gravitational effects on nearby matter. Gas falling into a black hole heats up and emits X-rays before crossing the event horizon. Binary systems where a black hole is pulling gas from a companion star are bright X-ray sources. The first stellar mass black hole detected, Cygnus X1, was discovered this way in the 1960s. Today, we've detected dozens of stellar mass black holes in our galaxy and have indirectly confirmed the existence of millions more through gravitational wave observations of black hole mergers. Black holes are the ultimate endpoint of stellar evolution for the most massive stars, cosmic graves where matter is compressed beyond recovery, where the very fabric of spacetime is warped so severely that not even light can escape. They're predicted by Einstein's general relativity, confirmed by observation, and represent one of the most extreme consequences of gravity in the universe. The first stars in the universe were different from stars today. They formed about 100 million years after the Big Bang, when the universe was still young and contained only hydrogen, helium, and trace amounts of lithium. No heavier elements existed yet because no stars had lived and died to produce them. These first stars, called population III stars, were likely much more massive than typical stars today, perhaps 100 or even 1,000 times the Sun's mass. They formed from pristine gas, untainted by heavy elements. The absence of heavy elements affected the cooling of the gas clouds, allowing only very massive stars to form. These stars burned incredibly hot and bright, living only a few million years before exploding as supernovae. Their explosions seeded the universe with the first heavy elements, carbon, oxygen, iron, and others, paving the way for later generations of stars, planets, and eventually life. We've never directly observed a population III star. They existed so long ago and were so far away that their light is incredibly faint and redshifted. But future telescopes like the James Webb Space Telescope may be able to detect them, revealing what the first stars were like. Understanding population III stars is crucial for understanding the early universe, the origin of heavy elements, and the chemical evolution of galaxies. These stars represent the beginning of the stellar story, the first lights in a universe that had been dark since the cosmic microwave background was released 380,000 years after the Big Bang. They transformed the universe from a simple mix of hydrogen and helium into a chemically complex environment capable of producing planets and life. Star formation is an ongoing process. New stars are being born right now, in regions like the Orion Nebula, a massive cloud of gas and dust about 1,350 light-years from Earth. The nebula is visible to the naked eye as a fuzzy patch in Orion's sword, below the three stars of Orion's belt. Through a telescope, it reveals a chaotic nursery of young stars, glowing gas, and dark pillars of dust where more stars are forming. The trapezium, a group of 4 bright stars in the center of the nebula, was born only a few 100,000 years ago. These stars are still surrounded by remnants of the cloud they formed from. Their intense ultraviolet radiation is ionizing the surrounding gas, causing it to glow with the characteristic red light of hydrogen. Over time, the radiation from these young stars will blow away the remaining gas, and the nebula will fade, leaving behind a new cluster of stars. Stellar nurseries like the Orion Nebula are scattered throughout the galaxy. They're found in the spiral arms, where gas is compressed and triggered to collapse. Each nursery can produce hundreds or thousands of stars over a few million years. Some of the most dramatic star-forming regions are the giant molecular clouds, vast structures containing enough gas to form millions of stars. The Carina Nebula, for example, is one of the largest star-forming regions in the Milky Way, home to some of the most massive and luminous stars known. Star formation is a continuous process, replenishing the galaxy with new stars as old ones die. The rate of star formation in the Milky Way is about 1 to 3 solar masses per year, meaning enough gas is converted into stars each year to equal the mass of 1 to 3 suns. This rate has varied over the galaxy's history, with bursts of intense star formation during mergers with other galaxies, but it's been relatively steady for the past few billion years. Stars rotate, and their rotation affects their shape. The Sun rotates once every 25 days at its equator, though different parts rotate at different speeds because it's made of gas, not solid material. The poles take about 35 days to complete one rotation. This differential rotation is driven by convection in the Sun's outer layers and creates complex magnetic fields that lead to sunspots, solar flares, and coronal mass ejections. Some stars rotate much faster than the Sun. Vega, a bright star in the constellation Lyra, rotates once every 12.5 hours. Its rapid rotation causes it to bulge at the equator and flatten at the poles. If we viewed Vega from the side, it would appear noticeably oval rather than spherical. The equator is about 23% larger in diameter than the poles. Fast rotation also affects a star's temperature. The poles, being compressed, are hotter and brighter than the equator. Vega's poles are about 10,000 Kelvin, while the equator is about 7,600 Kelvin. This temperature difference makes the star appear different depending on the viewing angle. We happen to see Vega nearly pole-on, which is why it appears so bright and white. If we saw it edge-on, it would look dimmer and slightly redder. Rotation rates vary widely among stars. Some, like white dwarfs and neutron stars, can rotate hundreds of times per second. Others rotate so slowly it takes years to complete one rotation. Rotation affects a star's magnetic field, its activity level, and even its lifespan. Fast rotation can increase magnetic activity, leading to more star spots and flares. It can also affect the star's internal structure, changing how heat is transported from the core to the surface. Understanding stellar rotation is important for modeling stellar evolution and for interpreting observations of distant stars. The star Eta Carinae is one of the most massive and unstable stars known. It's about 100 times the mass of the Sun and 5 million times more luminous, shining with the light of 5 million suns. Eta Carinae is so massive and so bright that it's barely stable. It exists on the edge of what's possible for a star, where radiation pressure is nearly strong enough to blow the star apart. In the 1840s, Eta Carinae underwent a massive eruption, briefly becoming the second brightest star in the sky despite being 7,500 light-years away. It ejected about 10 to 15 solar masses of material, forming two lobes of gas that still surround the star today. These lobes, called the homunculus nebula, are visible through telescopes as a distinctive hourglass shape. The cause of the eruption is still not fully understood, but it may have been related to instabilities in the star's outer layers or interactions with a companion star. Eta Carinae is actually a binary system, with two massive stars orbiting each other every 5.5 years. When they approach each other, their stellar winds collide, creating a shock front that produces X-rays and possibly triggers smaller outbursts. Eta Carinae is expected to explode as a supernova soon, though soon, in astronomical terms, could mean any time in the next 100,000 years. When it does, it will likely be one of the brightest supernovae in recorded history, possibly visible during the day and bright enough to cast shadows at night. The supernova might even produce a gamma-ray burst, a narrow beam of extremely energetic radiation that, if pointed toward Earth, could affect our atmosphere. Fortunately, Eta Carinae's rotation axis is not aligned with Earth, so any gamma-ray burst is likely to miss us. But the supernova itself will be spectacular, a once-in-many-lifetimes event visible to anyone on Earth. Stellar nurseries are often shaped by the stars they create. Massive young stars emit intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow. This radiation also creates pressure, pushing gas and dust away and sculpting the nebula into intricate shapes. The pillars of creation, a famous feature in the Eagle Nebula photographed by the Hubble Space Telescope, are columns of dense gas and dust where new stars are forming. The pillars are being eroded by radiation from nearby young stars, slowly evaporating away. At the tips of the pillars, small globules of denser material resist the erosion longer, protecting the gas behind them and creating the pillar shapes. In a few million years, the pillars will be gone, completely dispersed by the relentless radiation. But for now, they're stellar incubators, with new stars forming deep within the dense gas, hidden from view in visible light but detectable in infrared. The Eagle Nebula is about 7,000 light-years away, so the pillars we see today are as they were 7,000 years ago. In fact, some astronomers estimate that the pillars may have already been destroyed by a supernova shockwave, but because the nebula is 7,000 light-years away, the light showing their destruction won't reach us for thousands more years. We're seeing the past, preserved by the time it takes light to travel. Stellar nurseries are dynamic environments, constantly changing as stars form, grow, and begin to affect their surroundings. They're some of the most beautiful objects in the galaxy, glowing nebulae filled with the light of newborn stars and the shadows of collapsing clouds, cosmic landscapes where creation is ongoing. Stars can collide. In dense star clusters, where thousands of stars are packed into a small volume, collisions can occur. When two stars merge, they form a single, more massive star. This star is often bluer and hotter than the surrounding stars because it has more fuel to burn and is essentially a younger star despite being in an old cluster. These blue stragglers stand out in old globular clusters, where most stars are red and cool, having exhausted much of their fuel. The presence of blue stragglers was once puzzling. How could young, hot stars exist in ancient clusters? The answer is collisions and mergers. Blue stragglers are not young, they're rejuvenated, the product of two old stars combining into one. The collision itself is a violent event, though it happens slowly by human standards. Stars don't smash into each other like cars. Their mutual gravity causes them to spiral together over weeks or months as they orbit each other ever more closely. Eventually, their outer layers merge, and the cores coalesce into a single object. The merger releases a tremendous amount of energy, possibly creating a brief outburst of light and ejecting some mass into space. The resulting star is more massive than either progenitor and will burn its fuel faster, appearing younger and bluer. Stellar collisions are rare in the galaxy at large. Space is vast, and even in crowded regions, stars are far apart. But in the dense cores of globular clusters, collisions are more common, perhaps occurring every few million years. They represent an unusual evolutionary pathway, creating stars that wouldn't exist through normal processes. Studying blue stragglers helps astronomers understand both cluster dynamics and stellar evolution in high-density environments. The night sky we see is shaped by the seasons and Earth's rotation. Different constellations are visible at different times of year because Earth orbits the Sun, changing our view of the surrounding stars. In summer, the night side of Earth faces different stars than it does in winter. Orion, for example, is a winter constellation in the northern hemisphere, visible in the evening from roughly November to April. In summer, Orion is in the sky during the day when the sun is up, so we can't see it. Similarly, Scorpius is a summer constellation, visible in the evening from May to September. Earth's rotation also means the stars appear to move across the sky each night, rising in the east and setting in the west. This motion is an illusion. It's Earth that's rotating, not the stars moving. But from our perspective on the surface, it looks like the entire sky is turning around us. Stars near the celestial poles, the points in the sky directly above Earth's poles, never set. They circle the poles throughout the night and throughout the year. Polaris, the North Star, is always visible from the northern hemisphere because it sits nearly on the north celestial pole. In the southern hemisphere, there's no bright star at the south celestial pole, but the constellation Crux, the Southern Cross, never sets for observers far enough south. The changing sky was crucial for ancient astronomers and navigators. By observing which constellations were visible, they could determine the time of year. By observing the positions of stars throughout the night, they could tell time and determine directions. The sky was their calendar and compass, and understanding its patterns was essential for agriculture, navigation, and religious ceremonies. Today, we rarely rely on the stars for these purposes, but the patterns remain, a connection to our ancestors and a reminder of our place on a turning planet orbiting a star. Some stars are surrounded by disks of gas and dust. These are called protoplanetary disks, and they're the birthplaces of planets. The disk forms as a byproduct of the star's formation. As a collapsing cloud of gas spins faster, conservation of angular momentum causes it to flatten into a disk. The star forms at the center, and the disk surrounds it, orbiting the young star. Over time, particles in the disk collide and stick together through a process called accretion. Dust grains stick together to form pebbles, pebbles stick together to form rocks, rocks form boulders, and eventually these clumps grow large enough that their own gravity takes over, pulling in more material. These growing bodies are called planetesimals, and they eventually become planets. The entire process takes a few million to a few tens of millions of years. Our solar system formed this way, from a disk around the young sun about 4.6 billion years ago. By studying protoplanetary disks around other stars, astronomers are learning how planetary systems form and how common they are. The Atacama Large Millimeter Array, ALMA, a radio telescope in Chile, has captured stunning images of protoplanetary disks, revealing gaps and rings where planets are likely forming. One of the most famous is HL Tauri, a young star only about 1 million years old, surrounded by a disk with multiple dark rings. These rings are probably cleared by forming planets, sweeping up material as they orbit. Observing these disks is like watching our own solar system's history, seeing the process that led to the formation of Earth and the other planets. Protoplanetary disks also contain complex organic molecules, the building blocks of life. These molecules are delivered to planets as they form, potentially seeding them with the ingredients necessary for life. Understanding protoplanetary disks is crucial for understanding not just how planets form, but also how common the conditions for life might be in the universe. The Sun will eventually eject its outer layers, forming a planetary nebula. This has nothing to do with planets. The name is a historical accident. When astronomers first observed these glowing shells of gas through early telescopes, they looked round and planet-like, so they were called planetary nebulae. In reality, they're the ejected outer layers of dying stars, illuminated by the hot core left behind. A planetary nebula forms when a red giant sheds its outer layers at the end of its life. The star's outer envelope becomes unstable and drifts away, expanding into space. The hot core, now exposed, emits intense ultraviolet radiation that ionizes the expanding gas, causing it to glow. The result is a beautiful, expanding shell of colored gas. Different elements emit light at different wavelengths, creating the varied colors seen in planetary nebulae. Hydrogen glows red, oxygen glows green and blue-green, and nitrogen glows red. The specific colors and patterns depend on the composition of the gas and the structure of the nebula. Planetary nebulae come in many shapes: round, elliptical, bipolar, and even more complex forms. The shape depends on factors like the star's rotation, magnetic fields, and whether it has a companion star. Some planetary nebulae are nearly perfect spheres, like the Able 39 planetary nebula. Others are bipolar, with two lobes extending in opposite directions, like the Butterfly Nebula. Some have intricate, filamentary structures, like the Cat's Eye Nebula. These nebulae last for only about 10,000 to 50,000 years before the gas disperses into the interstellar medium, enriching it with the heavy elements created by the star. The hot core left behind is a white dwarf, which slowly cools over billions of years. Planetary nebulae represent the final gasp of stars like the Sun, a brief but beautiful phase that marks the transition from active star to stellar remnant. They're also laboratories for studying the late stages of stellar evolution and the return of material to the interstellar medium, completing the cycle of star birth, life, and death. We've covered a lot of distance tonight, from the smallest red dwarfs burning for trillions of years to the massive blue giants that live fast and die young, from the formation of stars in vast nebulae to their deaths as white dwarfs, neutron stars, or black holes, from the quiet fusion in stellar cores to the catastrophic violence of supernovae. Billions of light years, billions of years, trillions of stars, each with its own story. But here's the thing, you're not separate from any of this. The atoms in your body were forged in the cores of stars. The oxygen you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood, all of it was created through nuclear fusion inside stars that lived and died billions of years ago, long before the Sun or Earth existed. When those stars exhausted their fuel and exploded as supernovae, they scattered these elements into space. The shock waves from those explosions compressed nearby gas clouds, triggering new rounds of star formation. One of those clouds eventually collapsed to form the Sun, and the leftover material formed the planets, including Earth. You're not just learning about stars, you're made of stars. The atoms in your body are stardust, forged in the cores of dying suns that burned billions of years ago in parts of the galaxy far from here. Every element heavier than hydrogen and helium in your body came from a star. Some came from stars that died peacefully, scattering their outer layers into space as planetary nebulae. Others came from stars that died violently, exploding as supernovae and seeding the galaxy with heavy elements. You are literally made of the remnants of ancient stars, your body a collection of atoms that have journeyed through the cosmos for billions of years before coming together to form you. And it's not just you. Everything around you, the ground beneath your feet, the air you breathe, the water you drink, the buildings, the trees, the animals, it's all stardust. The Earth itself is made from material created in stars. The Sun is creating new helium right now, fusing hydrogen in its core, just as billions of other stars are doing throughout the galaxy. Some of those stars will die tomorrow, cosmically speaking. Others have already died, and we just don't know it yet because their light is still traveling toward us. The cycle continues. Stars form, stars live, stars die. Their deaths seed the formation of new stars, new planets, and perhaps new life. The universe recycles itself, transforming hydrogen into helium, into carbon, into iron, into planets, into you. Every time you look up at the night sky and see a star, you're looking at a distant sun, perhaps with planets of its own, perhaps with life gazing back at us. You're seeing the past, because the light from that star left years or centuries or millennia ago. You're seeing nuclear fusion, the process that powers every star and creates the elements necessary for life. You're seeing gravity and quantum mechanics, the forces that govern how stars form and how they shine. You're seeing the universe at work, creating and destroying, transforming and recycling, endlessly cycling matter and energy through space and time. If you're still awake, there are more videos waiting. But if sleep found you somewhere along the way, then this worked exactly as it should. Rest well, knowing you're part of the same cosmos as the stars, made of the same stuff, governed by the same laws, connected to everything by the shared history of the universe. See you next time.